Okay, I think we have talked about the degree of polymerization so far. So I just wanted to summarize what we have talked about in terms of the equations. Okay? As you all know, from the Carrodus equation, we knew that degree of polymerization is equal to 1 over 1 minus p, where p is the extent of reaction. So if you increase the conversion or extent of reaction, then it becomes the high number because if it's getting closer to 1, then you have a very small number here, so that it will increase the dP. Okay, and for the polycondensation reaction, if you consider the functionality, then you have to think about the functionality here, where F is the number of functional groups in your monomer. Okay, we assume that in this Carrodus equation, the functionality is equal to 2. Okay, but if the functionality is over 2, then you have to consider this equation. Now, I told you about the meaning of this 2 here, because the 2 is required because if you have a AB type of monomer or AA or BB type monomer, then the reaction only occurs with A and B reaction. Okay? AA or BB will not be reacting to become a polymer. So you have to have only 2 functional groups reacting to become a polymer. So this is the convention. But we can modify this equation here, where dPn is equal to 2, where F could be average functional group. Average functional group. If you have a large number of functional groups in here, I think we will talk about in here in terms of the network polymers. Okay, so last time I think we have talked about this dPn here, where the R is equal to the feed ratio, where if you have A functional group and B functional group, and the number of functional groups in your monomer is defined as Na, and number of functional group of B is defined as NB, and if you have a little bit of excess of a B functional group, then R will be less than 1. Okay, so you can control the excess amount of the A monomer or B monomer so that it could be related with the feed ratio. If you put this feed ratio in your dPn, dPn will be modified to this equation right there. So dPn will be 1 plus R and 2R, 1 minus P plus 1 minus R. Here. And if P, this is 1 minus P. 1 minus P here, that equation. So if P is equal to or close to 1, then you have to cancel this out. It will become 1 plus R, 1 minus R. So if you know the feed ratio, where if R is equal to less than 1, such as if you have a 1% excess of this B functional group, so that R will be 0.99. If R is 0.99, then you have a decrease in this number here, so that you will increase the dPn. And this way, I think you can control the molecular weight of the polymer, and this is what we have talked about so far. Okay. Now, this equation can be applied to other network step polymerization reactions. So, for example, we have so far talked about the linear polymers, but you can make the cross-linked polymer or network polymers using the multifunctional monomers. Okay, for example, if you have a glycerol is a little bit of a sweet, sweetener, and it's different from glycol. Glycol contains a 2 hydroxyl group, so it will be a CH2OH and CH2OH. So if you have this terminology with hydrogen, it is called the ethylene glycol. And this one, it contains 1 more methylol. This is called the glycerol. Okay? And glycerol has 3 hydroxyl groups, so you have a 3 functional group in your 1 monomer. And glycerol, if you have glycerol reacting with any carboxylic acid, it will become network polymer. So we call this as an alkyl type of polyester, okay, if you have a glycerol in there. Phenol, as already mentioned, we have 3 functional groups in here because of the hydroxyl. Hydroxyl in benzene ring will be a ortho-directing or para-directing the functional group, so that you have 3 sites for your further reaction. Melanin formaldehyde resin can be also cross-linked to the polymer. You have 3 amine groups, and this hydrogen will be acting as the one of the functional groups. So this is regarded as a hexafunctional. So formaldehyde can react with one of these hydrogen, and you have just like a star polymer, it will become very highly network polymer in 3-dimensional way. Okay? So 3 functional or trifunctional, and hexafunctional if you consider your functionality. So in calculating your degree of polymerization, you have to think about the F average in this case. Okay? So I will show you how we can calculate in one of the examples. Now, before we go into the detail, you have to know about the gel point. The gel is different from Zol. Okay? Zol is a solution stage, whereas gel is in a gel stage. Well, a little bit of a semi-solid state, and such as a gelatin. If you have a jelly or gelatin, it's not solid. Okay, it's not solution. So it's in between this the gel is in between the solid and liquid, and at the gel point, the viscosity increases all of a sudden. Okay, viscosity increases very slowly, but at the gel point, it increases all of a sudden, and this is what we call the gel points. And at gel point, as I said, it becomes from liquid to the solid or to the gel. And finally, the bubbles. If you have any bubbles in your solution, you can see the bubble is rising. Okay, because the viscosity is quite low. But as viscosity increases all of a sudden, then bubble stays right there, and you cannot remove those bubbles. Okay? And those are the very typical, examples of the gel points. And finally, it's almost impossible to stir, impossible to apply the stress in your reaction medium, and you cannot react furthermore in the case. Excuse me. So at the gel point, what happened is that, this is a little bit of a complicated structure. At the gel point, degree of polymerization is almost infinite. Okay, degree of polymerization is infinite. If you have infinite situation, because we have a 2 which is constant in the denominator, these should be equal to 0. Am I correct? So at that condition, where at the gel point, dPn is equal to infinite, and in that sense, 2 minus F average, P is close to 0. So the we know F average, so at the P, in that case, will be a F average over 2. So this point is called the gel point conversion or critical conversion. Okay? At gel point, you can expect the gel point from the F average. So if you know the F average, the conversion to become a gel point will be calculated as well. Okay? Although I have elaborated a little bit more, this is what I'm going to tell you. So, for example, if you have a glycerol, we have 2 moles of glycerols. Let's assume that we have 2 moles of glycerol. So you have 6 functional groups here, right? 6 hydroxyl groups. If you have 3 moles of maleic anhydride, we have okay, let's say this is anhydride. This is called the anhydride. If you have a methyl group here, this is acetic anhydride. Okay, but if you have a benzene ring, we call this as excuse me. We call this as a maleic anhydride. Maleic anhydride has 2 carbonyl groups. So those 2 carbonyl groups will be cleaved to become a carboxylic acid type of the material. So hydroxyl can attack the carbonyl. Because of that, in a situation, maleic anhydride can be regarded as a bifunctional because you have 2 carbonyl groups to be attacked by the nucleophile, which is hydroxyl. So we have 6 moles of, 3 moles of maleic anhydride, which is bifunctional. So we have 6 functional groups in the left-hand side. We have another 6 functional groups in the right-hand side. F average can be defined as how many functional groups total divided by how many moles of the molecules that you have. Okay? So we have 5 moles in the denominator, and we have 6 functional groups of each. Okay? So average functionality will be about 2.4 in this reaction system. Okay? If you put F average 2.4 in the in here, okay, then you can calculate where is the point, where is the conversion percent that becomes gel point. Okay, so in that case, the calculated value will be about 0.83 or 2 divided by 2.4, but experimentally you can observe the gel point will be around the 77%. Okay? So it's not exactly the same, but you can at least calculate where is the gel point, so that whether you want it to be over the gel point or whether you want it to stop the reaction before the gel point. So you can determine gel point reaction in that case. I think this is the details of what I have just told you. Right? So at 83.3% of the conversion, it will be exactly the same as the gel point, but experimentally it's a little earlier than the calculated values. Anyway, you can modify this Carruthers equation if you have the more than to functionality in your system, so that you have to realize the importance of the gel point in the case of network polymerization reactions. Okay, so these are the summary of what I have described in Chapter 8 in this case. And from now on, I think I will describe to you some of the examples of the condensation polymers, okay? Starting from polyester, and I will talk about the polyamide and other aromatic polymers. First of all, the polyester. I think we have already talked about this polyester, but you can make this polyester by using the ester interchange reaction, okay? Because ester interchange reaction will be much more plausible, because the byproduct condensate will be the alcohol. So alcohol has a lower the boiling point than water if you use the acid in the case. So it will be much easier to remove this methanol as a byproduct rather than water, because methanol has a low boiling point. And in that case, you have to remove the methanol, because you wanted to obtain the product, which in this case is the diester, and you wanted to remove this. You wanted to obtain this polyester by removing this ethylene glycol in the second stage. So this is the real industrial the application of the ester interchange reaction to make the polyester. Polyester. First, the polyester was produced by DuPont in 1936, but it could be used as a fiber and films. Right now in Korea, we have about at least 4 or 5 polyester producers, including LG Chem, the Samyang, and all of those fiber manufacturers are making the polyester, and you all wear the polyester fibers. Polyester has as you know, the ester linkages or functional groups, but this ester functional group does not provide a lot of the water, the hydrogen bonding with water. Right? So polyester itself has a little problem about the electrical charge issues. So in the winter season, I feel like I have a lot of electricity coming from my body when I wear the polyester fibers. So be careful if you have any allergy to the electricity in the case. But anyway, the polyester fibers can be used as the garments or the industrial fabrics. You can make a very thin nanofiber out of this polyesters, so that you have many applications. You can make also the films out of this polyester. I think about 10 years ago, we used the overhead projector, where we use very thin polyester films, and we can write something so that you can use that instead of this projector. Okay? So long time ago we used it, but it's all gone. But anyway, the polyester films are still used in many of the industries. Not as many as before, as I mentioned, because of the digitalized society. We do not use the films right now because of digital camera, but a long time ago we used the films. Those films were made of polyester. Right? If you go to the hospital, look at the X-rays. X-ray films are made of polyester films. Right now, I don't think they're using the polyester films, X-ray films, as many as before, because of the digital, the reading processings. Anyway, the polyester fiber can be manufactured mimicking the cellulose, right? Mimicking the cellulose, mimicking the leathers as well. Okay, you can make a polyester you can make a the leather like garment from polyester. Okay, it's like an artificial leather. Okay? It's not real leather, but it looks like a leather. It feels like a leather, but it's made of polyester. Okay? 폴리에스테르로 가죽 같은 걸 만들 수가 있어요. 뭐 세무라는 거, 세무 가죽 같은 거 이런 거 있는데요. 그런 거를 폴리에스테르로 또 만들어요. 이게 만져보면 가죽 같아. 근데 가죽이 아니라 폴리에스테르. 그렇게 아주 이제 굉장히 극세사, 아주 굉장히 가느다란 파이버, 극세사라는 걸 만들어 가지고 폴리에스테르로. 그래서 셀룰로즈 같은 또는 그 실크 같은 또는 아주 가죽 같은 그런 필을 할 수 있는 그런 것까지도 이제 발전해 있습니다. Well, nylon 66 can be made by two-step reaction. I think we have already talked about this. We have hexamethylene diamine reacting with adipic acid to become the first step to become a salt. And the second step, you remove the water by pulling the vacuum at high temperature so that the amidation reaction can be occurred in this case. This is the aliphatic polyamide, okay, aliphatic polyamide, because we have the aliphatic linkages between the amide groups. Remember that if you have a short number here versus the large number, you have a different hydrogen bonding capability, so that glass transition temperature or melting temperature might be different. Okay? So we have talked about this property of different, the bonding capability as well. Anyway, this is the typical example of nylon 66, and nylon is manufactured, of course, in Korea as well. If you look at the company name called Kolong was first found in the early 1960s. That name came from Korea Nylon Company. Okay? And if you make a short, it becomes a Kolong, okay? Korea Nylon Company. and they first produced this nylon in Korea in the 60s, and they become a big company as well. Okay, so this nylon can be, of course, the fiber. Nylon can be the plastic as well. Now, if you put the aromatic groups instead of aliphatic, okay, it will become very rigid. Okay? Particularly in this case, amide group linkage is linked in the para position of the aromatic group, so that you have a very rigid material. Okay? Because para position 1 is a linear structure. Okay? Whereas if you put amide group in the meta position here, it's a little bit of a kink structure. Okay, and the linearity is not formed, just like what you can see here in this case. So the para positioned group here can be a very rigid material, and you can make a very strong Kevlar plastic or fiber out of this aromatic polyamide. Okay? This is the Kevlar, which was a yellow fabric that I have shown you in the first time, yellow fabric, so that it could be a bulletproof the fiber that you can make. It's stronger than steel, so that using those fiber out of this Kevlar, you can make a parachute strings, or rope for the ships. Okay, if you look at the ship, when they park in the port, they have to use a big steel rope, made out of the steel or metals, but it's too heavy. So they started to replace this, rope, steel rope with the Kevlar, the fiber rope, and you have a lot of applications of this Kevlar as well. Now you can see much more about this. We call this aramid as a short name. Aramid, aromatic amide is a short name of this the Kevlar fiber, or Nomex fiber, which I will tell you in the next slide. And you can make a very strong aramid the polymer, and you can look at the other sites as well. First produced by DuPont in 1950s, and it has already been 60 years after starting producing this Kevlar fiber. Nomex is the name of this metaphenylene isophthalamide. If you have a meta-substituted diamine and meta-substituted carboxylic acid, you can make her very similar to Kevlar, but different configuration. Okay? So the Nomex is the commercial name of this polymer. It has less strength than Kevlar, but still it has a very high thermal stability because of the aromatic ring and the amide ring in the backbone structure. Okay? But it's less it has a less strength, but of course a little bit of flexibility. So I think I showed you this fiber, which is in the white color. Right? This fiber is quite flexible, quite soft, softer than Kevlar fiber. So if I will use to cut this fiber, the Kevlar fiber, by using a scissor, I will be very my hand is quite hot when I cut this Kevlar fiber by using a scissor, whereas Nomex, I think it's okay. Anyway, you can make this the fiber out of the polymer, and in some cases you use lithium ions, lithium chloride or something, in making the spinning the fiber in this case. We have the fourth example is polyimide structure. Polyimide structure. I think you all know the polyimide structure because it's been tested in the first exam. Imide structure has the 5-membered ring with the 2 carbonyls with amine groups here. Now what we can make is that we have you see, this is the maleic anhydride, okay? But if you have one more anhydride here, this is what they call the pyromaleic dianhydride, or PMDA, okay? And we can have many types of dianhydrides as well. We can make different anhydrides. We can make different diamines. Now, if you change X and Y, okay, X could be methylene, S could be hexafluoro groups, S could be sulfone, S could be carbonyl, okay? And Y could be the same as well. You have a very different kinds of dianhydrides and diamines. Okay? And by using different combination of this X and Y, you can make a different type of structure of the polyimides. Okay? Now this is a very typical example, and this is the first polyimide that we have made. Okay, so what you can make is also a two-step reaction. Okay? First step is that you react with anhydride and the diamine in the solvents such as DMAC or DMS or NMP. And first, by storing this 2 monomer in the solvent at mild temperature, the temperature could be about 50 to about 70 degrees C, then you come up with the amic acid. Okay? We have this amine will attack this carbonyl, and it opens this carbonyl and the oxygen, the bonds, and it becomes amide, and carboxylic acid is still left. So we have 2 acids and amide, and what we call this is the amic acid. Okay? Okay, this is the polyimide film. And the color is a little, dark brown, because there are 2 reasons for this color. Because this reaction, after this reaction, the amic acid, you increase the temperature up to about 300 degrees C. Okay? If you increase the temperature up to about 300 degrees C, and by pulling the vacuum to remove this water, because you have a carboxylic acid and carbonyl, so this N will attack this another carbonyl here, and OH group, and H from NH will become water, and it will be a ring closure reaction. The second reaction is called a ring closure reaction by applying the vacuum at high temperature to remove this water. And this is called the polyimide film, or called the Kapton film. Kapton film. So this is the example of the Kapton film. Kapton film has a little dark yellow or the dark brown structure because of the conjugated structures. Conjugation means that the double bond is alternatively connected to each other. Right? Now, we have a double bond, but it doesn't have any double bond here. But you have one unshared electron pair, which may act as a double bond, so that you have a double bond, electrons, double bond, electrons, double bond, stuff like that. So, because of this conjugated structure, if you look at the UV spectrum, the absorbance will appear at a little higher the wave number, so that it imparts this color. Okay? But this film is insoluble if you already make this the polymer structure. In other words, it will not become amic acid. Okay? Irreversible reaction, because there are a couple of reasons, but I think they react this to become polyimide structure at high temperature, which is about 300 degrees C. And although I express this as a linear polymer, it's not really a linear polymer, but you may have a little bit of thermal cross-linking. Okay? So thermal cross-linking at high temperature produces the insoluble Kapton films. You can also make the fiber as well, okay, out of this the polymer, but not in this structure. Now, we have a PMDA and the aniline reaction to make the insoluble polyimide, but insoluble polyimide is not very well described in the electronic industry. Now, this Kapton film or the polyimide is widely used in electronic industry to make passivation of your electronic devices or semiconductor. But what they have done was to coat this polyamic acid on top of the silicon wafer, and there is a lot of photoresist overlaying on top of this polyimide. But they later on they removed this polyimide structure at high temperature, but you remember that you have evolved the water out of the semiconductor production, which may cause some of the defects in producing your semiconductor. So in the semiconductor industry, they need a soluble polyimide rather than making the imide out of this polyamic acid. Okay? So soluble polyimide can be produced from different combination of this polyimide structure. So you can make a soluble polyimide by adding, such as a 6F group here and 6F group here to make this polyimide, or ketones or sulfones. Okay? By using different, polyimide, different anhydride and different amines, you can make a soluble polyimide so that you can dissolve the polyimide and coat on top of the silicon wafer so that you can remove the solvent rather than water. Okay? Okay. I think we have described here the first step is polyamic acid formation. Polyamic acid is formed around 70 degrees C, and then cyclized this polyamic acid over 150 to about 300 degrees C, okay, by thermal imidization reaction. And this aromatic polyimide is very highly heat resistant, and typical is a Kapton or etch film. Okay, you can make a soluble polyamic acid or soluble polyimide by changing your X link or Y linkages, okay, by using this CH2 or sulfone or 6F group or any breaching groups or biphenyl groups. You can further investigate what's going on about this polyimide using the various websites. Aromatic polysulfone. Aromatic polysulfone is the other example. Aromatic polysulfone has a structure something like this. You have a sulfone structure, okay, but this sulfone is connected with the aromatic ring in the para positions. But not only the sulfone, but you have other functional groups as well, such as ether. Okay? Now this sulfone provides the solubility, but ether group provides the flexibility. But you have aromatic rings, so it's a little bit of complicated properties. Okay? It's not very strong polymer, but it has a very functional polymers. Polysulfone was first produced by Union Carbide in America under the name of Udel, the commercial name of Udel, but it was sold to Amoco because about 30 years ago there was a very big disaster, the explosion of the chemical company in India. We call it as a Bhopal accident, and they have to. Union Carbide has to provide the funds to compensate the patients. So they have to sell this Udell business to Amoco, but Amoco was not as good as before. And Amoco has done the business for about 20 years. But right now, the Solvay acquired this business, and they have a plant in the Georgia. And right now, from yesterday until today, we have a guest from Solvay Specialty Polymers from Georgia as well. And we will have a meeting in this afternoon because we have a project with these guys. Anyway, this polysulfone polymer is produced by, right now, Solvay Specialty Polymers in Georgia plant. And this polysulfone is widely used as engineering plastics, okay? Meaning that it has a very high strength compared with the aliphatic polymers, so that polysulfone can be used to make plastics for special purpose, or the large quantity of this polysulfone was used as a membrane for separation purpose. Okay? Well, you have a water purifier in every household. Water purifier, 정수기. Okay? Water purifier can be made out of this polysulfone in the form of hollow fiber or in the form of a flat sheet. Okay? We have a larger customer for this polysulfone in this case. So you can take a look at the polysulfone. You can hit the polysulfone in the website and take a look at who is producing these polysulfones as well. The reaction occurs between the bisphenol A, sodium salt of the bisphenol A, with the dichlorothiophenyl sulfone, through this polycondensation reaction, of course. So this ether group will attack this point, and so that you produce the sodium salt, and it will become the polysulfone reaction. The sixth example, the last example, will be the formation of the polybenzimidazole. This polybenzimidazole has also the aromatic linkages, okay, as you can see here. Instead of diamine, we use tetramine and diacid, okay. And the simplest description of the polybenzimidazole is just removing the water from here, but it's not that simple. But in the next slide, you have two-step reactions. But the final structure is imidazole. We have N and NH group, which is 5-member ring. This is called imidazole ring. We have a benzene ring connected to imidazole, is the general name of the benzimidazole. Okay. This benzimidazole was first produced or first invented by Professor Marvel in the Arizona State University back in 1960. Okay, 1961, and he published the first article. So it's been already over 50 years. Okay. This polybenzimidazole has a very high thermal stability. The glass transition temperature is over 450 degrees C. So it's not soluble and meltable. And this PBI is the general name. This PBI was not the flammable. It's not bond. Okay? It's a self-extinguishable, the fiber. Self-extinguishable means that if there is a fire on your wood, okay, or cellulose, or the paper, you notice that this fire, although the flame is gone, you still have the fire, you still have the burning procedures, okay. But in this case, the PBI, although you have you started to burn this fiber, okay, it's not propagating this burning procedure, but it's just gone. If the flame is gone, the fire is gone. Okay? This is what we call self-extinguishable. Self-extinguishable the characteristics. Or we have a dissipating, heat dissipating aspect. Heat dissipating. Heat dissipation. Dissipation means that if you have a flame, then if you wear the fabric, okay, or if you coat your space shuttle, okay, and inside of the space shuttle or inside your fabric, we have a human being, and human beings should be protected, of course, from the vehicles. And if you have a fire and the heat is penetrating through the vehicles or through the coating, then the human being will receive a lot of heat shocks, right? But that's not very desirable, property. If the heat or temperature or heat is dissipating, if it's going out instead of penetrating through, will be a very desirable property. And this PBI has a heat dissipating property, so that although the space shuttle, when it's coming from the space to the Earth, you have frames, and that's good because heat will not be going into through and shocking to the human being, but it's gone out. So the PBI was used in that purpose as a coating material of the space shuttle, or could be used as a firefighter's protective clothing. Because a firefighter or 소방수, firefighters need the protection, okay, from the fire. So if you have a fire here in this room, if the baby is inside of you in the room with a fire, there is somebody should go inside of the room and take the baby out with the protection. Okay? If he has a protection, then one will be able to go inside of the room and take the baby. But if you don't have any protection, I don't think nobody will go inside. So PBI was widely used as firefighters' protective clothing, or the parachutes, or the pilot. Okay, pilots. The clothing, protective clothing, or the race driver, okay, F1 race drivers' protective clothing can be made out of this PBI fabrics. Well, the manufacturing process is not this simple. If you have tetramine reacting with the acid ester, then it becomes a little bit of a complicated structure. But you have a amide-amine structure, just like amine acid structure in the case of polyimide, and it becomes a cyclization at around 400 degrees C to become benzimidazole. Okay? This is the typical example of the benzimidazole formation. But anyway, he was very successful. Professor Malville was very successful. And again, if you can change the tetramine, if you can change something here, or if you can change something here in between, you can have a large variety of benzimidazoles. And he filed the patents, and the Celanese company, licensed his technology, and they started to produce this from 1966, along with the NASA, and but this fiber was later on produced by the Celanese back in 1979, And I was involved with my PhD thesis with these polybenzimidazoles. Yes, we have provided the information about this, and but this polybenzimidazole was very difficult to make because of the side reactions. This tetramine, if you have two amines of each point, the reactivity is not the same, so that you often face with the gelation problem because of the different reactivity of the amines. And so you have to very carefully control this synthesis reaction conditions. Anyway, these Celanese licensed this PBI technology back in 1966, and it's not burning. It has a self-extinguishing property, but it's still very expensive, which is not very good. But anyway, right now the German company called Fixed bought the Celanese. But anyway, we have the company called the PBI Performance, and you can take a look at this website and see what's going on. Okay. This PBI is widely fabricated into the fiber so that the clothing, protective clothing, can be manufactured out of this PBI. But you can make the very functional films, which is called membrane, so that you can separate the proton and can make the membranes for fuel cell at very high temperature. That's one of the applications. And also you can make a separating membrane at high temperature, particularly for hydrogen. Okay, so hydrogen can be separated, and you can take a look at if you look at this website, you can take a look at the other applications as well, and they describe this here in this case as well. Next example is the epoxy polymer. Epoxy polymer is now this is three-membered ring is an epoxy. Okay? Three-membered ring is an epoxy. Epoxy, three-membered ring here in this case. This is called the epichlorohydrin. And the second monomer is called bisphenol A, which is the commercial name. Okay, bisphenol A and epichlorohydrin. You can have a reaction between this Cl and the hydrogen. So you remove this HCl, and it will be connected to each other very simply. And the reaction will proceed further. Okay? At the end of the chain, you have an epoxy group here, and which is the linear polymer. Now, this is one component. This is the one component. But you have a hydroxyl group as well in between. Okay? This hydroxyl group, along with the epoxy, can be cross-linked to become cross-linked network polymer by using cross-linking agent. Okay? For example, if you have an anhydride, such as maleic anhydride or acetic anhydride, and you have many hydroxyl groups in those linear chains, these linear chains will be connected to each other by using two functional or bifunctional monomers, the cross-linking agents. So you have many networks, okay, in three-dimensional way, so that it becomes a cross-linked polymer. So epoxy, I think you have you can perhaps hear about this epoxy. In the subway, sometimes you can see the epoxy adhesive can be sold, maybe 1,001, okay, because the company was broken or something, and they're selling this epoxy. But you have two tubes generally if you wanted to apply this epoxy the adhesives. The first one contains this linear polymer. First tube contains the linear polymer, and second tube contains the cross-linking agent. So that first component, linear polymer, and the cross-linking agent mixed together. Okay, mixed together, and apply those mixture with the two broken parts. If you wanted to put this and this together, you apply the mixture, okay, and apply the pressure, and put it into a little bit of oven or at the room temperature for several hours, and it becomes very, adhere to the property. So you can put this together, which is called the adhesives. And epoxy can be used that purpose. I mean the adhesive purpose, or epoxy can be utilized as a coating, okay, as a coating material. If you look at the gas station or gasoline station, the floor has a little bit of a different color. Or if you look at the laboratory inside, the color is a little different. And if there is any chemical, floating around, including gasoline, you have to protect your floor with the coating which has a chemical resistance. Okay? So epoxy coating can be used in that purpose. Okay? So curing agent might be maleic anhydride, phthalic anhydride, or the pyromaleic dianhydride and others, or the diamines as well. And right now, I think in Korea, the Kukdo Chemical Company is the largest company manufacturing these epoxy resins. Okay? They are worldwide and global company. I think although it's small, they export a lot of these epoxies to U.S. And when I was working at 3M in U.S., I think we buy this epoxy from this Kukdo. Okay? So Kukdo Chemical Company is producing this epoxy anyway. It's a thermoset resin. Thermoset means a cross-linked polymer, and it has a very high chemical resistance and solvent resistance, so they can be used as a coating purpose, and you have a very good adhesion property, so that it will be used as adhesives. It has impact strength. It has a structural application as well. So epoxy can be utilized in many of the applications. Okay. We can make unsaturated ester. We can make unsaturated ester, including, glycerol with the phthalic anhydride. And if you react this is bifunctional, as I said. We have a trifunctional glycerol. If you add third monomer containing carboxylic acid with unsaturated group, okay, unsaturated group, then finally you can come up with the unsaturated group terminated structure. But because of the glycerol, you have a network structure. Okay, network structure. If you heat it up, this double bond can be also opened to become the cross-linked network structure. Although it's a polyester, because we have a network polymer, we have a cross-linked polyester, okay, containing unsaturated the functional groups. This unsaturated functional group can be made by using other type of monomers as well. Although this looks like a linear polymer, but if you have a double bond here, it could be further cross-linked. And this is what we call the unsaturated polyester. Polyester is not only the linear polymer, but you can make a network polymer by using multifunctional monomer or by using unsaturated group containing the monomer. Anyway, if you make the polyester with the network structure, the property of this, the unsaturated polyester, is that it has a quite brittle structure, quite brittle. It's not soft. Softness or brittleness depends upon the cross-linking density. How many of the cross-linking sites, what is the cross-linking, how many cross-linker that you use will influence the brittleness or softness of your materials. Well, the application of this, the unsaturated polyester, is that widely used is the bowling balls or bowling pins, bowling balls, the helmets, okay, helmets, or the fishing rod, okay, fishing rod, or tennis, the rackets, or golf clubs, the home appliances, meaning that in 가전제품이라는 뜻입니다. Home appliances and kitchen floorings and so on, and you can make a lot of those the applications by using this polyester containing unsaturated groups. Perhaps the last example is the polycarbonate. Okay? Polycarbonate. Polycarbonate can be made using this chemistry. Well, the second monomer is what? Second monomer is called bisphenol A. The first monomer is called, well, you have, let's see, because we have a little bit of time. This is called formaldehyde. This is called formic acid. Formaldehyde is quite toxic, whereas the formic acid can be produced from our body as well. From our Krebs cycle, we produce formic acid. Okay? If you drink the alcohol, it will be oxidized to become aldehyde, which is acetic aldehyde, and becomes acetic acid, right? The acetic acid itself is okay, alcohol is okay, but aldehyde will give you headache, right? So anyway, this is not very good. It's quite reactive. That's why the formaldehyde will react with the phenol to become bakelite, react with the melamine to become melamine formaldehyde resin. It will become a urea formaldehyde resin, okay, to become reacting with urea. Now, if you change this H with chlorine, this is much more reactive than formaldehyde. Okay? We call this as a fourth-gen gas, fourth-gen. Okay? This fourth-gen is very reactive, much more reactive than the formaldehyde. And fourth-gen gas, if this is a monomer, this is a gaseous form. Gas was used to kill the Jews by Hitler back in 1930s and 40s. So fourth-gen gas is very toxic, should be very careful, but very reactive. Okay? This fourth-gen, of course, will react with the alcohol, so that the O will attack this carbonyl, so you produce HCl, and of course, another OH will be. So you can very closely, reacting with this OCO, and if you have O, we can have a carbonate functional group. Okay? So ester with ether will produce carbonate group. And this was first produced by General Electric under the name of Lexan. Tg is about 150. Melting temperature is about 270. This Lexan has a very good property, such as a transparency. Okay, it has a very transparent property, so that those glasses right now these days where you're wearing is all made of let's say Lexan, okay? Or PMMA or polymethyl methacrylate. So PMMA and the polycarbonate are the two major plastic used for these glasses. Okay? PMMA has a little problem because of the impact strength, but this polycarbonate has a good property. It doesn't have any grazy property. Grazy means after a long period of use, you have a little cracks. Okay? 플라스틱이 왜 이렇게 약간 갈라진 것 같은 거 있죠, 오래되면. 그런 PMMA인데 이건 없어요. So that it's widely used as glasses. And of course, the pilots, they have to wear the big transparent glass, and it's all made of polycarbonate. This polycarbonate is one of the very good properties of transparency, and you can imagine what kind of the applications that you have. It has a very good impact resistance, packaging, phone dial and rings, and so on. Phone dial rings, perhaps it's not very widely used right now, but a long time ago, if you look at the telephone, a long time ago they use two different plastics, right? It's not connected, but you have a speaking speaking part and the hearing parts. So you have to use the two hands. But it's good to have, if it's connected, it's good. Right? But ring, long time ago, we used to use rings, okay, phone dial rings, which should be transparent, okay, to look at the number so that you can dial them. And the plastic that they use is a polycarbonate. That's why General Electric is not a plastic company. A long time ago, it was founded by Edison about more than 100 years ago, back in perhaps 18 something, in Schenectady in New York. But they started to use this, they need some more plastics because of the evolution of the new product, okay? Such as telephones, such as electrical parts and turbines. Mechanical part needs the plastic. That's why they started to develop their own the plastics. And this is one of the plastic they have invented at the time. But this Lexan was sold to Saudi company right now called the SABIC, S-A-B-I-C, Saudi company. And Lexan is produced by the SABIC right now. It's produced by a two-stage reaction under the vacuum. And if you heat it up at 300 degrees C, you can produce this polycarbonate. I think that's all, this time. I think we can finish some of the other the parts of the polycondensation reaction next Wednesday. Any questions? Okay, if not, have a nice weekend, and I will see you next Wednesday. Okay.